Hi, this is a video on radioisotopes and types of radioactive decay. So before we can really talk about all of these different types of nuclear reactions, which are the nucleus itself actually changes, which is not in a, doesn't happen in a normal chemical reaction. But we do need to kind of review some of the atomic structure that we did at the beginning of the term one. So we know we have atoms, the smallest units of matter, and then in the atom, in the nucleus, we have the protons and neutrons, which have a mass of 1 AMU, or atomic mass unit. And then we have the electrons, which are in the electron cloud outside of the nucleus, and essentially they have no mass. So if we look at our periodic table, there's information on here about some of this. So like if I look at this, atomic number is the same as the number of protons. That's what identifies that element. So if it has 80 protons, it's mercury. There's no other element it can be. The mass number is not found on the periodic table. The mass number is the sum of the protons and the neutrons. It's going to be a whole number. This is an average of all the different isotopes or kinds of mercury. So here's an example of 3 types or isotopes of carbon. There's carbon 12, and this is the mass number, carbon 13, and carbon 14. So when we look on the periodic table, we can see that carbon has an atomic number of 6. So it has 6 protons. So the mass of this one is equal to those 6 protons plus 6 neutrons. That's how we would get to 12 there. And then this carbon 13 still has 6 protons, but it's going to have 7 neutrons. And this carbon 14 still has 6 protons, but now it has 8 neutrons. Just a little bit more review. So we also remember we can write the symbol of the element with the mass number up here and the atomic number here. This way you get a little bit more information than you did in the previous slide. So if I see it's carbon 13, I know it's going to have 6 protons. The atomic number is 6, the mass is 13, and then I can subtract and see, indirectly that there are 7 neutrons, or I can subtract and see that there's 8 neutrons in this type of carbon. So why are some things radioactive and they break up and other things are not? So there's a video here that really explains this in a simple but really a good way. So I'll have you guys watch this video.
This lesson looks at why some isotopes are radioactive. You may wish to refer to the lesson Why Aren't All Atomic Masses Whole Numbers to help you understand this video. The identity and chemical properties of any atom are determined by the numbers of protons in its nucleus. As atoms get bigger and heavier, the nuclei get bigger and heavier, and the protons need a sort of nuclear glue to help hold them together. Neutrons provide this glue and prevent the positive charges of protons from repelling each other, thanks to something called the strong nuclear force. Elements can exist with slightly different numbers of neutrons, and we call these isotopes of an element. It is particularly common for heavier elements where a lot of neutrons are required to hold the nucleus together, but smaller and lighter examples include the isotopes of hydrogen. Hydrogen-1, hydrogen-2, also called deuterium, and hydrogen-3, also known as tritium, are the 3 isotopes of hydrogen. They have 0, 1, and 2 neutrons respectively. Tritium is the heaviest isotope of hydrogen as it has a larger mass number. Note that in each of these isotopes there is a single proton. This means that the element is unchanged, and that's the important point. It is still hydrogen and will react chemically in exactly the same way. There is often more than one stable isotope of an element. In fact, much of the world around us is made up of stable isotopes. However, sometimes there aren't enough neutrons in a nucleus, or there may be too many for it to be stable. An analogy is a person carrying boxes. If you try to carry too many boxes, you'll end up dropping some. And if you continue, you'll keep dropping boxes until you reach a manageable amount. This is your stable state. And nuclei behave in a similar way, and they will try to stabilize themselves. If there are too many protons or too many neutrons, the nucleus can spontaneously rearrange itself and throw out particles in the process. This is essentially what happens in radioactive decay. Isotopes that have unstable nuclei like this are known as radioactive isotopes or radioisotopes. In our hydrogen examples, tritium are unstable and are hence radioisotopes of hydrogen. The more unstable a nucleus, the faster it will try to rearrange itself into a more stable state. And another name for this process is radioactive decay.
And that leads us to talking about, there's 3 common types of radioactive decay. So this is what, and these are not normal chemical reactions, these are nuclear, which means the nucleus itself is going to change when these radioactive decays happen. So we're going to talk about 3 common ones. So the first type of decay that we're going to talk about is alpha decay. And alpha particle is this helium. It's a helium atom, but it's not because it doesn't have electrons. It's just like a helium. It has mass of 4, has atomic number of 2, so those numbers on the side still mean mass on the top, atomic number on the bottom. And this is what happens when a nucleus overall is just too big. So it will kind of try to rearrange and get itself to be more stable by emitting an alpha particle. So then when you look at the way to this shows up in So when we look at this, we as a reaction, we can see the mass number of this beginning element, radium, is 226, and the atomic number is 88. When that alpha particle comes out, now the mass of 4 came out of this, and 2 of that mass are protons. So I'm going to take this 226 and I'm going to subtract 4 to get the new mass of the new isotope that's formed. I'm going to take this atomic number and subtract 2 to figure out the new atomic number. That's the part where then, because it has a new atomic number, it's now a new element. And I can look on the periodic table, atomic number 86, and then I can find the element radon. So let's do one example together. So this is uranium-238. It has a mass of 238 and 92 protons. Uranium is down here on our periodic table. So it's an alpha decay, so I'm going to write that alpha particle with a mass of 4 atomic mass units, an atomic number of 2, and because it has an atomic number of 2, that's why we use the symbol helium, and that is the alpha particle. So then we need to figure out what our new isotope is here. So what we would do is take 238 minus these 4. So the mass number of the new element would be 234. And then the atomic number, the protons, minus 2 means there's 90 left. And then when I look for an atomic number of 90, I find this element, thorium. Another really common type of radioactive decay is beta decay. In this one, a neutron actually changes into a proton. So if I look at the example here, the mass number doesn't change because the mass is protons and neutrons together, but the atomic number goes up by 1 because a neutron is changed into a proton, so it goes up by 1. This is the beta particle. It's like a fast-moving electron, so we do use an E for that electron. Has 0 mass. And then we put a negative down here because, not because it has a negative atomic number, but when we use that number, we can add the -1 and the 54 to get the 53. So this number always equals the sum of these numbers. And same thing for the mass number. It's going to equal the sum of the mass numbers on the other side. So we'll talk about beta particles and how these can affect people and things in just a moment. So let's do one example here. So let's write our beta particle, and then let's think about what would be the number here. So what plus 0 is going to give me 14? It's going to still have the same mass of 14, but what plus -1 will give me 6 is 7. Then when I look for atomic number 7, I see that it is nitrogen. Gamma decay is a type of decay where the nucleus doesn't change necessarily. It does usually accompany another alpha or beta decay, but it's not going to change the mass number or the atomic number of the element that we start with. And then the gamma ray or gamma particle itself is represented like this. So it's the Greek letter gamma, which looks kind of like a fish, has 0 mass, and we don't need to put, it's basically, we call it a particle, but it's really just pure energy. So the thing that we're going to ask is that you can recognize what type of decay that you're looking at. So I want you guys to pause the video and try to identify whether these 6 reactions are alpha, beta, or gamma decay. So if you did these with me, you can check. This is going to be an alpha decay because we have that alpha particle. This is a beta decay because we're making a beta particle. This is also alpha. This one is gamma decay because we get the gamma particle. So is this one. And then lastly, this one is a beta decay. So might be, it's really interesting now, these 3 different types of particles, they're also called radiation. Which type of radiation is going to be the most harmful to a human and why? So the alpha particles are pretty big in the world of chemistry. Because of that, they don't last very long. They can't go through as much, so we're not that worried about them. Our clothes and our skin can stop them. However, if you were to ingest something that undergoes alpha decay, those alpha particles inside of your body, you have less layers of skin, so then that could be a problem for your health. Beta particles are much smaller than alpha particles, so they are much more able to penetrate or go through things. They can go a few meters in the air, and they can be stopped by things like metal and glass. And then lastly, we have gamma radiation, which is the one that is the worst, has the highest penetrating power. It is able to go right through human body and flesh and cause problems with our DNA, which can cause different forms of cancer. So gamma radiation is very difficult to stop. We attempt to stop it with feet of concrete and inches of lead. So the most penetrating, able to cause harm and go through things and affect them is gamma. The least penetrating are alpha particles that come from an alpha decay.